Ever wondered how a binary search tree works? Let's dive into it. A binary search tree, often abbreviated as BST, is a unique structure used in computer science to hold data. It's a binary tree, meaning each node has at most two children, commonly called the left child and the right child. But what sets it apart is its inherent ordering property. For any given node n, all values in the left subtree of n are less than n, and all values in the right subtree of n are greater than n. This simple yet powerful rule allows us to perform complex operations like searching, insertion, and deletion with great efficiency. It's like having a well-organized library where you can quickly find, add, or remove books. Now that we have a basic understanding of what a binary search tree is, let's explore its operations. First on our list of operations is search. Imagine you're in a maze and you're trying to find a specific room. You start at the entrance, and at each junction you make a decision. You choose a path based on some criteria. Maybe you always take the right path, or maybe you follow the signs. Searching in a binary search tree, or BST for short, works in a similar way. You start at the root of the tree, which is the entrance to our metaphorical maze. Now, you're looking for a specific value, so that's the room you're trying to find. At each node or junction, you make a decision based on the value you're searching for and the value of the current node. If the value you're looking for is less than the current node's value, you move to the left child of the current node. It's as if you saw a sign saying all values this way are less than the current value. On the other hand, if the value you're looking for is greater than the current node's value, you move to the right child. It's like the sign now says all values this way are greater than the current value. This process continues until you either find the value you're looking for, or you reach a node that has no children. If you find the value, great! You've successfully searched the BST. If you reach a node with no children, and it's not the value you're looking for, then the value you're searching for isn't in the tree. It's like reaching a dead end in the maze and realizing the room you're looking for doesn't exist. The beauty of search operation in a BST is its efficiency. On average, it takes logarithmic time, which means as the size of your tree doubles, the time it takes to search only increases by one step. That's pretty fast, wouldn't you agree? And that's how search operation works. Let's proceed to the next operation. Next up, we have the insertion operation. This operation is key to expanding the binary search tree, allowing it to accommodate more values. Remember, our objective is not just to insert a new node, but also to maintain the ordering property of the binary search tree. So how does this work? Well, we begin at the root of the tree. If the tree is empty, the new node becomes the root. If the tree is not empty, we compare the new value with the value of the root. Now, there are three possibilities. If the new value is less than the root's value, we move to the left child of the root. If the new value is greater, we move to the right child. But what if the new value is equal to the root? In most binary search trees, we either move to the left or the right, depending on the specific rules of the tree. We continue this process, moving down the tree until we find an empty spot where the new node should go. This spot will be either a left or right child of a node, and voila, we've successfully inserted a new node into our binary search tree. But what's so special about this process? This method of insertion ensures that the ordering property of the binary search tree is maintained. Each step we take, whether to the left or the right, is based on a comparison that preserves this property. This is what makes the binary search tree so efficient for operations like searching and sorting. In terms of complexity, the insertion operation has a worst-case time complexity of O(n), where n is the number of nodes. This happens when the tree becomes unbalanced and starts to look more like a linked list. But on average, you can expect a time complexity of O log n, which is quite efficient. So, there we have it. That's how we perform the insertion operation in a binary search tree, ensuring that our tree remains ordered and primed for efficient searching and sorting. With the insertion operation done, let's move on to deletion. Now, we come to the deletion operation. In a binary search tree, the deletion operation can be a little more complex than search or insertion. This is because we need to ensure that the tree retains its properties even after a node is removed. The process involves three possible scenarios. The first scenario is deleting a node with no children. This is the simplest case. We essentially just remove the node from the tree. Since it doesn't have any children, we don't have to worry about reorganizing the tree. The second scenario is deleting a node with one child. In this case, we remove the node and replace it with its single child. This ensures that the binary search tree property is maintained, allowing us to continue with operations like search or insertion. The third scenario, which is the most complex, involves deleting a node with two children. Here we can't simply replace the node with one of its children. We have to find a suitable replacement that maintains the binary search tree property. This is usually done by selecting either the largest node from the left subtree or the smallest node from the right subtree, also known as the predecessor or successor respectively. Once we have identified this replacement node, we swap it with the node to be deleted. Now we are back to having to delete a node with at most one child, which brings us back to the first or second scenario. As you can see, deleting nodes in a binary search tree requires careful consideration to maintain the tree's structure. But once you understand the mechanics behind it, it becomes a straightforward process. So to sum up, the deletion operation in a binary search tree involves checking the node's children, replacing the node if necessary, and continuing this process until the tree's structure is preserved. That wraps up the deletion operation. Let's proceed to the last operation. Finally, let's talk about traversal. Traversal in a binary search tree is a systematic way of visiting or traversing all the nodes in the tree. The order in which the nodes are visited defines the type of traversal. There are three common types: in-order, pre-order, and post-order. Let's start with in-order traversal. In this method, we first traverse the left subtree, then visit the root, and finally traverse the right subtree. This order of traversal ensures that the values are visited in ascending order, which can be particularly useful in certain applications. Next, we have pre-order traversal. In this approach, we first visit the root, then traverse the left subtree, and finally traverse the right subtree. This type of traversal is often used in scenarios where the action to be performed is from parent to child, such as when creating a copy of the tree. Lastly, we have post-order traversal. Here we first traverse the left subtree, then traverse the right subtree, and finally visit the root. This order of traversal is useful when the children must be processed before the parent, such as when deleting the tree. Each type of traversal serves a unique purpose and can be used in different scenarios based on the problem at hand. But regardless of the type, all traversals are crucial for accessing and manipulating the data within a binary search tree. Remember, the key to mastering traversals, like any concept, lies in practice. So don't shy away from coding up these algorithms and trying them out on different trees. And that's a wrap on traversal. Let's summarize what we've learned. So what have we learned today? We've delved into the world of binary search trees or BSTs, a special kind of binary tree data structure. We've seen how each node has at most two children, a left child and a right child, and the ordering property of BSTs, that all values in the left subtree of a node are less than the node, and all values in the right subtree are greater. We've also explored the four main operations on BSTs: search, insertion, deletion, and traversal. We've seen how these operations maintain the ordering property of BSTs, and how they have an average time complexity of O log n, making them highly efficient. And finally, we've walked through a Python example to implement a binary search tree, demonstrating how the operations work in practice. And that's a binary search tree for you. Thanks for joining us, and stay tuned for more interesting topics.